Ball and stick models are inevitably challenging, especially when you can't move it around to see what's going on. I think you guys will notice in this structure that we have a lot of hydrogens visible. Like here's a methyl carbon, right? And actually this is CH2, and this is CH2, and CH2, and CH2. But this carbon right here, how many hydrogens does it have? Tough. If that one hydrogen that could be attached to it is underneath the carbon, you wouldn't see it. You wouldn't know that it's there. But if there's no hydrogen attached, you wouldn't know that. If you could rotate this and you could see that this carbon is connected to all the other three groups planar, then you'd know there's no hydrogen attached. And if there's no hydrogen attached, what charge does it get? Positive charge. But the ball and stick model, it's really hard to convince yourself there's no hydrogen there that you just can't see, and it doesn't show the charge. So the trick is that it tells us that this is a carbocation. The carbocation shown below. Where's the positive charge? It doesn't explicitly state it. Well, it can't be at any of these positions that have full octets, so the cation must be on the carbon that has 3 explicit bonds, but I don't see a 4th, so that must be where the positive charge is. Now, it says that this is an intermediate in a reaction with HCl with 2 different alkenes. We learned last week that the HX addition, hydrohalogenation reaction, starts with an alkene and consumes the pi bond, as addition reactions do. So the question is, what possible alkenes can I have? Well, the first step of the HX addition reaction is an acid-base step. What's the acid? Between an alkene and a hydrogen halide reagent, like hydrochloric acid, hydrobromic acid, what's the acid? The HCl. And what's the base? The alkene. And so if this is the intermediate and the alkene was the base, that means that the intermediate is the conjugate acid. So I need to start with an alkene, I need to add a hydrogen, and I need to have a positive charge. The carbon that holds the positive charge, that's the carbon that lost the pi electrons. So where is the carbon that used the pi electrons? Jordan, I think you've got too many carbons in that ring. Oh, you're doing a different problem? No, I think you got too many carbons in that ring. This carbon must be involved in the alkene. It's the carbon of the alkene that lost the pi bonds and didn't get the hydrogen. What other carbons could have been in the alkene? The methyl carbon could have been in the alkene. Remember that we kind of described the alkene as an alpha beta, 2 carbons adjacent to each other with a degree of unsaturation. So if maybe alpha is this carbocation and beta is this methyl, I just draw a double bond between them. Gabby, is this still a CH3 at the end? No. It becomes a CH3 in the reaction when it acts as the base. Remember, that's what this first step is doing. It's putting a hydrogen onto the alkene. Where else could the double bond have been? With the tertiary carbon and with what? Jordan? Either of the carbons in the ring. Okay, but doesn't that mean that I could have had 3 different products? One when the alkene is to the left, one when the alkene is to the right? They're the same. It's just differing by rotating it, flipping it like a pancake. Yeah? If you were to name the alkene where it forms with the carbon on the left versus the carbon on the right, they would have the same name. They're both 1-methyl cyclopentene. And that's what I was trying to point out to you, Jordan, was you picked the cyclohexene structure. Same exact molecule, just differed by flipping it over. Now, to be fair, you could argue that there is another base that can actually get to this structure as well, but it would require a carbocation rearrangement. If I showed 3-methyl cyclopentene, and I reacted this with HCl, there's only one carbocation that can form. These 2 carbons are equally substituted. So which one is more likely to be the base? Which one is more negative? Neither. Both are more likely to be the base. So I have an even chance of either of them being the base, and it doesn't matter which of them is the base, because the carbocation that forms is the same, just flipped over like a pancake. And now I realize that I lied. Sorry. This was not the alkene that could give a carbocation rearrangement to this. This alkene forms this carbocation no matter what. This carbocation is surrounded by carbons of equal substitution. Carbocations trend in stability with substitution. The more substituted, the more stable. And in fact, bonds can shift over if it will leave in its wake a more stable carbocation. Nothing will shift here because the only thing that forms is an equally substituted carbocation. There's no energetic gain by a rearrangement to either of these carbons. So this alkene does react, it just doesn't give us this carbocation intermediate. Okay, so what's the alkene that I was going for? Well, there's really only one other choice. That's 3-methyl cyclohexene. I had drawn 4-methyl cyclohexene. All right, here's another problem. When 3-methyl cyclohexene acts as a base, which carbon is more likely to be the base? Which carbon is more negative? They're both equally likely because they're both equally substituted. We only get this partial negative, partial positive across an alkene when one of them is less substituted versus more substituted. You guys remember this? Positive charge has more moral support. It has more electron density swarming it, protecting that positive charge. Less substituted, it has less electron repulsion. So it's more likely to do something with the electrons. If it takes electrons, it has less electron density pushing those electrons away, so it can use them. Where's the partial negative, partial positive here? It's hard to predict. They're equally substituted, so both could happen. If this carbon out here reacts with the HCl, I actually get this carbocation again. It's placed 1, 2, 3 carbons away from the methyl group, 1, 2, 3 carbons away. But there is another carbon that could also act as the base.
So you're saying that top one is the same as that one because it's just flipped, right?
Correct. Sorry. This carbocation that forms here is the same as this one, just on the other carbon, because that would just be rotating it. But at this position, I have a secondary carbocation. Do you guys agree with that? The carbon is bonded to 2 other carbons, and it's a cation. So secondary carbocation. And it's adjacent to a tertiary carbon, which would be more stable as a carbocation. And bonds are not stagnant. Bonds are not sticks. Bonds are always vibrating, compressing, bending, wagging, twisting, moving ever so slightly. And if this bond between the tertiary CH bumps a little bit to the left, those electrons will get sucked into that new position, leaving in its wake a more stable carbocation. What did we name this last week? When a hydrogen takes the electrons and shifts over on a structure? Hydride shift. Do you recognize how that last three letters, "ide," suggests a negative charge? How do you get a negative charge on hydrogen? You need to give it 2 electrons. Hydrogen with no electrons, positive. 1 electron, neutral. Hydrogen with 2 electrons, hydride. It's like H minus driving the electrons over, leaving in its wake a positive charge. You remember that idea of standing in a line? I stood in the TSA line Thursday morning at 4:30 for 2 hours. Fun stuff. And as the line moved, new holes were created where people were moving out of and new people were moving into. But I would never show the hole moving. If I were trying to display this hydride shift, I would never use an electron arrow to say the lack of electrons is moving to that positive carbon. What? I would never use a gap in the TSA line to say this hole is going to move over here. Holes don't move. Things move into holes and leave new holes behind. That's what we show with a hydride shift. Why does it do it? Energetic stability. Becomes more stable. Why does a ball roll down a hill? Energetic stability. Okay, that was a challenging one. Just in my opinion, because it's hard to interpret the structure. The other one is similar, right? This one gives us another ball and stick model, except this time we have the product. So instead of the intermediate, we have a product of HX addition. So I see the X is that red ball. The halogen has been added somewhere. That suggests to me, assuming a hydride shift has not taken place, it suggests that that carbon was a part of the alkene and has now had a new group added to it. What's the substitution of that carbon? Tertiary. That carbon's attached to 3 other carbons. Are any of them symmetric like we saw here? This tertiary carbon was symmetric to 2 sides. Is that tertiary carbon symmetric? No, the secondary carbon on the right is different than the secondary carbon on the left, because on the left it's closer to this methyl group, and on the right it's not close to a methyl group. And then of course I've got this ethyl chain. So here I had a tertiary carbon, but I said there's only 2 reasonable starting materials. How many for this? This carbon has to be involved, which means the carbon on the left could be involved, the carbon on the right could be involved, the carbon off the ring could be involved. 3 different starting materials. All following Markovnikov's principle, by the way. H adds to the carbon with more H, and the halogen adds to the carbon with less H, all giving us the same product. 3 different structural isomers, identical product. Did that answer that question? Do you feel like you can tackle it now? No? Do you want to see one of them? So let's start with my ring, and I've got this ethyl chain, and then I've got this methyl. and I'm dealing with this tertiary carbon. I know I want that carbon to be a part of the alkene. So now the choice is, do I show the alkene to the left, to the right, or down? Just pick a spot, draw that double bond. You've got your first structure. Sorry, I can't really show the alkene. Cool. We're going to spend more time on reactions, more time on intermediates, more time on mechanisms, more time on reagents. I do have to give you guys some warning right now. On your unit test this weekend, you get access to your notes. And you guys know that I don't like lockdown browsers, so that means you have access to the world of resources. I recommend using your notes, because your notes are what I'm giving you, and your notes are what I'm kind of going to be testing you on. I'm not testing you on what you can find on Google. You can find a lot of stuff on Google. I also recommend that you try your best not to rely on your notes while you take the test, but come back to your notes to validate what you understood and what you remembered. Yeah? I recommend practicing these reagents, memorizing them, utilizing them, becoming familiar with them. I say memorize, but I really mean familiarize. Don't just look at it over and over and over, but use it in different contexts, use it in different ways. I've given you guys a start to that. I also have all of my old homework materials, all of my supplemental homework materials. You have extra practice problems on active. Familiarize yourself. Use the reagents. Spend time with this stuff. Because when it comes to the final, if you don't recognize it, you're SOL. And I don't want you guys to be stuck out of luck on the final. I want you to have that familiarity with the reagents. They're weird chemicals for some of you, so you have to spend time to make them make sense.
Can you go over the last one and why it attaches to the second carbon and not the first carbon in the carbon chain? The very last problem in the homework.
Oh, yeah, for section 7. What is the major product? Okay, so HX addition, which follows Markovnikov's rule. So I'm going to add H and I'm going to add Cl. This is the question you win. I'm going to add H and Cl across those 2 carbons of propene. You see why it's called propene? Where should H add? Markovnikov says add H to the carbon with more H. I have a CH2 and I have a CH. So I'm going to add H to the CH2 and make a CH3. Where does the Cl go? To the CH carbon. That is a regiochemistry principle. It describes where on a carbon chain you can predict groups to go. Yeah? But Markovnikov just came up with a nice little way to memorize where hydrogen goes, and he did nothing to explain why it goes there. Is it because hydrogen is attracted to other hydrogens? Is it because the hydrogens somehow stabilize the hydrogen going there? It's everything to do with charge stabilization. It has everything to do with the stability of that carbocation. So let me ask you this. Oh man, I look like one of those professors, don't I? The board just full of crazy stuff. If propene can form 2 carbocations, why doesn't it? If I can react propene with HCl, why can't I get both of these products? Calvin? No, I added H. Yeah, I added H here versus here. So if I add H to the secondary carbon, chlorine goes to the first. If I add H to the primary carbon, chlorine goes to the second. These are just structural isomers.
Because chlorine is too big or something?
Nope, doesn't have anything to do with the size of chlorine. But what this question is getting at is that only this happens. Allie? Allie? Kirsten?
Shot in the dark, but something with symmetry and
Symmetry is not a bad idea, but symmetry won't stabilize it here.
something with a charge.
Gabby?
More substituted.
What is?
The carbon's more substituted.
More specifically, the carbon with?
The charge has two carbons attached to it versus the one on the left only is connected to one carbon.
Perfect. The carbocation is more substituted. Why does that matter? A positive charge is a strong magnet, okay? It's going to pull in anything with a negative charge or even a partial negative. If I can weaken that magnet, if I can shield that magnet, I can actually make it more likely to form and slower to react, which is part of why it's more likely to form. This is very challenging to form. The energy for it is like this. Let me show that in black instead of in red because I've highlighted the correct answer in red. But to form the carbocation that is more substituted takes less energy. So it's going to happen. Do you guys remember my skee ball analogy? Did that make any sense? If I throw this molecule up my skee ball ramp, which one is it more likely to get onto first? Which one is it more likely to fall into? The one with lower energy. This is not a normal skee ball ramp, though.
Why is it like that? I just feel like I have all these rules in my head right now and no explanation, so it's hard for me to remember.
What's your rule? More substituted carbocation, more stable. Because this carbocation is shielded by electron density. You want to see the electron density? Okay, get something at that positive charge. It's hard to. It's blocked by all these hydrogens. Get something at that positive charge. Much easier to. It's not shielded by as much.
Yeah, but that seems counterintuitive now because the chlorine bonded to it.
The chlorine bond's here. Yes, yeah. The chlorine will get to it. That is true. Because it is still, it's not stable. It's a reactive intermediate. This is the confusing part. I've seen students struggle with this semester after semester. Why am I looking for stability in something that is reactive, right? Why do I want the thing that's going to react to be stable if I want it to react? The thing is, I don't really want it to do anything. This is just what it's going to do. Maybe my skee ball analogy didn't make sense either because this doesn't do a good job of comparing their energies.
So the hydrogen is going to go to the less substituted carbon because it's easier?
Because it's easier for the secondary carbon to form with that positive charge. That positive charge is surrounded by a bunch of electrons, and so it forgets that it is a positive charge. Moral support, that's what I call it. But that positive charge still makes it reactive and sucks in the ion, the chloride, like a magnet. It's just what magnet is more feasible to make. That primary carbocation, it's just not feasible. The energy that it takes for it to even exist is astronomical. It can happen, but if there's something that is easier to make, that will happen.
So then when those cations do form, are they usually interacting with
Say that again, because it did, but I just missed some of it.
When the cation does form, so the option on the right is what we usually see. I can accept that that's more energy favorable.
Sure.
When wherever the cation is, that is what is like a magnet towards the chloride or the bromide or whatever it is.
Yep.
More so than hydrogen.
Well, hydrogen in this case is a positive ion if it forms.
I guess I'm just trying to figure out why
Yeah.
the hydrogen goes to the other one and the chloride goes to that one.
Remember that hydrogen and the halide have a dipole across them. That's going to predict how they interact with an alkene that also has a dipole across it.
The negative is going to be attracted to the positive.
Yeah,
Always?
always.
Okay.
You've played with magnets. I brought them on the first day, right? I can bring them back. I've got them downstairs.
So the hydrogen will never bond to that cation.
Correct. Unless you can give hydride, H minus, and to get a source of hydride is dangerous, but not impossible. It's just that hydrogen is not very electronegative. So to find an element that hydrogen is more electronegative than, for it to own electrons, is hard to come across, but we use them a lot. In fact, there's a reaction we'll see in a few minutes that is a source of hydride. We call it sodium borohydride. So we can give a partial negative to that hydrogen, in which case we can get the hydrogen to line up with the more substituted carbon, in which case we would break whose rule? We'd break Markovnikov's rule. And so we have reactions where we can change the partial charge on hydrogen and give a product that is anti-Markovnikov. This is what I don't like about Markovnikov's rule. It makes you think about the hydrogens and not the charges. It's all about the charges. In fact, all of the reactions that we're going to learn, all of the mechanisms that we're going to learn, it comes down to the partial charge and the full charge stabilization. Okay, this was a good review.
That makes sense. Sorry for everybody.
That's okay. In fact, why don't we go from here into the mechanism? So if you guys could please copy this down. If you like to copy down the charges, that's okay. The HX addition mechanism has 2 steps. It is a very simple mechanism. 2 elementary steps, 1 intermediate. You cannot show this as 1 step, despite being able to show it as 1 step. Oh, I had a chat with Gemini AI about asking why certain things seem feasible when students are drawing mechanisms. And the Gemini took some of my thoughts and it pushed back and said, you come up with a good point. Pushable versus plausible. There is a way for you as a student to take this structure and show it happening in 1 step. Pushable. The alkene attacks the hydrogen, the chloride takes the bonded electrons and attacks the alkene. Look, I did it. Why do I need 2 steps? If it doesn't matter that I can draw it in 1 step, why am I asking you to draw it in 2 steps? This is what we call pushable. Nobody calls it that, sorry. AI came up with that. This is the idea of it is pushable. I can show the electron pushing. I can show how the electrons would work to do it all at once. It's not plausible. Part of why it's not plausible is that it goes against kinetic studies. We know how these reagents work. We know that there are two steps. We know that there are rearrangements with HX addition reactions. And rearrangements can only occur if a carbocation intermediate exists. I'm not impressed that you can show the arrows needed to do it in one step. I'm impressed that you know it takes two steps. Okay, have you added the arrows? Think about what changes you see. Spot the difference. In step one, what bonds form, what bonds break? What direction are those bonds allowed to go? Where do my arrows start? Where do my arrows end? I've already given you the partial charges. Partial charges are useful because they tell you what you can expect. You can expect arrows to begin at a certain point, end at a certain point, be used by a certain element, be lost by a certain element. CL. Sorry, that's not what you were stuck on, huh?
No, I was just reading the board, sorry.
That's okay. Good work here, by the way. Starts at an atom. It's okay. Actually, what you're saying is this hydrogen's going to go here.
Mm-hmm.
I agree. How does it get that? How does it get there? It needs to be bonded. Where does it get the electrons for the bond?
Which one, the hydrogen?
When the hydrogen gets here, it needs to get a bond to be there. It doesn't own the electrons with chlorine. So that atom, or that arrow,
this way.
should go to chlorine.
So it should go.
From an electron source. Don't start at an atom. It's okay.
Okay,
There.
like that.
Start at the electron
then-
source. Notice how the bond that was partial negative to chlorine went to chlorine.
Yeah.
Notice how the bond that is partial negative to the less substituted carbon will be used by the less substituted carbon.
Okay.
It won't go to a partial negative atom. The partial positive.
It'll go away.
The partial positive is
show it.
saying it will lose
Like
that.
this?
Sure, but
I don't like that.
now I can't see that it's bonding to hydrogen,
Yeah.
so we just have it go to the hydrogen.
Okay. So like.
Yeah. Now, how do you know it's this carbon and not this one? Because we see it.
Yeah, we see.
It is really hard to demonstrate. Nope,
Backwards.
backwards. Good. No. I want to use that bond to hydrogen. Chlorine is going to get the electrons back. Notice how you actually don't show that bond breaking. Good. First step's good. Now you just need the second.
Kind of cross out a lot of things.
That's
So I
okay.
had it like that and like that.
It's perfect now. Yeah, before it was the opposite. Things didn't make sense there. This is good. This is good. This is a good start. But we're not showing the HCl bond break, and it needs to break.
Oh.
And then it's always bonds form from the more electronegative.
Oh.
Your arrow starts where there are no electrons. I need arrows to start from electrons. Good. Good. Perfect. Great.
Let's go.
Great job. This is okay. This is great. But this doesn't tell me how it forms a bond to the hydrogen. So instead of going onto that carbon, let's just have it go onto the hydrogen, which means we're using one arrow to show both bond breaking and bond forming. I want my arrow to start at an electron source, never at an atom, because these are electron arrows. Good. Now, this bond also needs to break, and a CH bond needs to form. So one arrow will be used to show the carbon-carbon double bond breaking and the carbon-hydrogen bond forming. Perfect.
When you draw your arrows, do you usually draw it like towards which way the hydrogen will go, or no?
I don't always,
matter.
but if you did, if that's what you're going for here,
Oh, I did it the opposite way.
that's right.
Whoops.
You don't have to, and it is challenging. How do you know which carbon is using it then? You know based on the structure you draw next. Then we see your arrow there. Great, this is perfect. Where does this arrow point to? The bond?
No.
Don't I want to form a CH bond?
Right here.
CH2, CH3.
Oh, I see. So then, would it start at?
Well, let's think about the HCl bond. Where is that one going to break? 2 hydrogen or 2 chlorine? Those are the only options. Right, so let's draw that arrow. HCl bonds, HCl breaks to Cl.
HCl breaks to C.
Yep, HCl bond breaks to Cl.
Like that?
Perfect.
Okay.
Well, you don't have the perfect. Perfect. Now I need to break the carbon-carbon double bond, so I'm going to have an arrow that starts from there, and I need to form a CH bond. I go from CH2 to CH3, I form a CH bond. So I need to have that arrow start where the bond breaks and point at the hydrogen where it forms a new bond. Did I give you guys? Good. I didn't see your, oh, that's the,
Yeah, so that I'm having.
where's your intermediate? Your arrow here, also it starts at an atom. These are electron arrows, so they should always start at a bond. Good, great. What you got, Selena?
I don't have anything.
You're close. Oh, no, sorry, that's what I gave you. So we need to see the HCl bond breaking.
So would it come?
You know, I notice actually your arrow here in the not plausible isn't quite like my arrow. Notice how my arrow
It comes from the bond.
starts at the bond, not the atom. Even though it's not plausible, it's still following our rules, which is it starts at an electron source. So I need to break the HCl bond, would you agree? Which way will those electrons go? Towards H or towards Cl?
I feel like Cl because it has too many, right?
We already know that it goes to Cl. That's why Cl is partial negative, because it owns the electrons. So when the bond breaks, start at the bond and point to Cl.
This one?
Perfect. We know the carbon-carbon double bond needs to break.
So this goes to this.
Perfect. Now can you show the nucleophilic attack?
I have a question.
Perfect. Yeah.
On the hydride shift, can
Yeah.
it only shift if it's one carbon away?
Yes. Yep. And I would show that arrow starting from the bond, not from the atom, because atoms don't move. Electrons move, allowing atoms to reposition. Did you spot the difference? Have you practiced that skill enough? Because it takes some time to really be able to do it quickly. What did you spot changing in the first step? What bonds break? Pi bond breaks. HCl bond breaks. What bonds form? Carbon-hydrogen forms. I've got 3 things happening. How many arrows will I need? Maybe 3, maybe 2. Maybe I can show 2 of those changes at the same time. HCl bond breaks, there's only one plausible way for this to happen. The reason chloride is partial negative is because it owns the electrons. So when that bond breaks, it breaks to the chlorine. Carbon-carbon bond breaks, I can now combine carbon-carbon bond breaking and carbon-hydrogen bond forming. How do I know which of these carbons used it? Partial charge is useful, or I just look at the structure that forms. Nucleophilic attack. I have a carbocation. That is an electrophile. It will accept electrons. A Lewis acid. And I have chloride. That is a nucleophile. What's wrong with this? It doesn't start from an electron source. It starts from a lack of electrons. It also doesn't show a nucleophile attacking. It almost looks more like an electrophile attacking. So instead, I start from my electrons, and I deposit my electrons at a vacancy. By the way, I'm also starting at electrons and depositing at a vacancy. The vacancy is sigma star, the anti-bonding orbital of HCl. I'm starting my electrons at my electrons. I'm ending at a vacancy. Starting at electrons, ending at a vacancy. Okay, on your worksheet, we went through one of these mechanisms on the third page. We went through the one on the right. And we saw that that followed step one, acid base, and it followed step two, nucleophilic attack, but it did not follow step 1A, carbocation rearrangement, because the carbocation that formed was already the most stable. So it wasn't going to rearrange. I want us to do the second mechanism. This is 3,6-dimethyl cyclohexene reacting with what? And giving us at the end 1-chloro-1,4-dimethyl cyclohexane. I sure do. Anybody else need one? You're welcome. You bet. What reagent do I need here? What change is happening across the pi bond? I've only taught you one reaction so far. HX addition. So what should X be? Cl. So over the reaction arrow, we need HCl for this mechanism. Okay, step one, acid base. What's my acid? HCl. So what's my base? Come on. It's okay, we can sit here. You know that functional group? The alkene? The whole functional group we're focusing on for this unit? That's the base. Base attacks acid and takes the hydrogen. Which carbon is more likely to use the electrons? Let me give you an example. When we did the propene, we said the primary carbon was more likely. The less substituted carbon was more likely. When we did the other mechanism worksheet, when we did the other mechanism here, when we did 3-methyl 2-pentene, we said the less substituted was partial negative. That's more likely to use the electrons and bond to the carbon. More substituted is more likely to lose the electrons and take the carbocation. Did I say bond to the carbon and not bond to the hydrogen? Sorry. What about here? Which one is more substituted? Neither. So which one is able to form the carbocation? Either. This molecule is symmetric though, so regardless of which way it goes, you get the same product no matter what. But sometimes you get a mixture of structures because it doesn't matter which carbon acts, and so both carbons do act. It's just down to the statistics of it all. All right, so I see the product has the chlorine on the top, and I know the chlorine comes in at the nucleophilic attack, so I'm going to leave the carbocation closer to the top, but I want to reiterate it's symmetric, and for this reaction, it doesn't matter what happens. When I form a carbocation, I should look out for carbocation rearrangements. So I'm going to put a question mark here. Last time, I did not see a carbocation rearrangement. Can anybody tell why? It was already the most stable carbocation. There's no energetic preference. And Ju asked this earlier, carbocations can only rearrange by one carbon. It can only rearrange with something adjacent to it because it depends on the bond shifting over in the breeze. Sure, but again, if I'd put it on the bottom, it would have just differed by rotation. Can this carbocation rearrange? Why would it rearrange? There's a tertiary carbon adjacent. I'm sorry, I forgot something up here. What did I forget? Chloride. And that chloride plays no role in this step. This step happens instantaneously, femtoseconds. All of the steps do. But this is very fast. Hydride shifts. The electrons between C and H shift over to the other carbon, pulling the hydrogen with it, leaving in its wake a more substituted, a more stable carbocation. Still reactive, but more stable. Now I see a nucleophilic attack. Let me see your arrow for the nucleophilic attack. Great. Great.
Hold on.
It's okay. It's okay. I'll come back. Mm-hmm. It's okay. Good. I want to say that some people on the internet don't show arrows for hydride shifts. And so if you give me a mechanism that requires a hydride shift and you just write over the arrow hydride shift, you don't show me the arrows.
So is that what that is on the rearrangement?
Yeah.
The hydride shift, the hydrogen is attacking or is moving to that lack of electronic space.
That's right.
And it's leaving a different hole on that tertiary carbon.
Like this. I want to see the H, and I want to see the arrow pulling the electrons. I don't want to see hydride shift over the arrow. I want to see the arrow pushing for it. Great job.
Yeah.
Nailed it.
I haven't gone there yet.
Great. Great. Awesome. Yeah, and I'm sorry, this worksheet was a little tight on space. So like under the nucleophilic attack, I didn't leave you a lot of space to draw it. Great work. You're going to add your arrow here?
Am I over here?
Yeah, see how an arrow starts at the CH bond and points to the carbocation, indicating that that hydrogen is shifting to that vacancy, leaving in its wake a new vacancy. Yeah? There was a hole here, but that hydrogen filled it and left a hole here. Now that chloride will fill it. Good. Good. You're just missing your nucleophilic attack. Show me the nucleophile attacking to give that final product. You got it. Yeah, you just need your arrow too. Yep.
Let me read.
That's it, Perla.
Okay.
I would start more at the negative charge itself, but that's good. Who else wants feedback? Who did I not look at?
That whole, yeah, it's gonna fill that
Good?
whole-
You got it?
Yes.
Good. You got it. All right. By the way, my plan for today is to get through the 4 reactions that we're learning mechanisms for. And then we can cover the rest of the reactions next week, next class, when it's just predicting reagents, predicting products. I do want to point out, this is my new format for teaching mechanisms, showing the elementary steps. Starting material, product. Now that becomes a starting material, product. Now that becomes a starting material, product. But what we just did earlier was showing this as a fully sequential process, not showing each intermediate as its own starting material, but showing everything fully sequentially. If you wanted to, you could even take what I have here and you could show it as a fully sequential mechanism. Just connect everything vertically. I'm leaving it up to you about how you want to practice these and report them on your tests and your exams. This takes more time because everything you draw, you have to redraw. But it's less cluttered, and it reinforces how many steps I'm expecting, which is why if you give me that pushable but not plausible, you did it all in one step, and you didn't reinforce that this has to be at least 2 steps, sometimes with a carbocation rearrangement. So I'm giving these to you as their elementary steps to make that abundantly clear. I also assign points to mechanisms based on how many steps there are. And then half of the points assigned go for adding arrows, half of the points go for adding structures. You could give me just the intermediates, and you would get half the points for a mechanism. Then you could add on the arrows to show how bonds are forming and changing, and you'd get half the points for a mechanism. That's how I decide to grade mine. Yeah?
Can I go back to the cation rearrangement, is that always like resolved or caused by the hydride shift?
No,
There are other ways to do that?
there are other ways.
Okay.
Yep, you want to see one?
No.
Oh, okay,
The hydride shift, sorry.
that's okay.
I just want to make sure I have this definition correct.
Yep,
The hydride shift always moves to an adjacent carbon, and will that always be in favor of more stability? So,
correct.
okay, so it would never.
Always adjacent carbons, always towards greater stability.
Okay, so it would never be to the like if it moved from the top right to the bottom right, it wouldn't make a difference. So
From a secondary carbocation to a secondary carbocation, no.
okay. Okay, now you can show me.
Okay, some other carbocations that occur. The methyl shift. The methyl shift will occur when there is no hydrogen that could shift over. Would you agree that it takes a lot more energy to relocate a CH3 over just an H? So this is less preferential over a hydride shift, but sometimes there is no hydride shift that can be done. But here a methyl can shift over to the vacant spot on the carbocation. This really happens the most on a quaternary carbon, because after a quaternary carbon loses a methyl, it becomes a tertiary. If a tertiary carbon shifted a methyl, it would become a secondary carbon. So again, it would be more energetically favorable and give better stability at the end for it to shift a hydride. Methyl shift relocates an entire methyl group. Yeah? Takes a lot more energy, so it happens only on those quaternary carbons when there is no hydrogen available to shift. Yes. This is the one that you don't need to know. I won't test on it, but it should make sense in the context of better stability. Alkyl shifts often happen in the benefit of better angles within rings. In our OChem 2 labs, we actually used to have an experiment that saw an entire phenyl group shift over, and that was because it then had a resonance stabilized carbocation. Anything with resonance is going to be more stable. But take, for example, this cyclopropane with a CH2 carbocation, primary carbocation. If this carbon inside the ring shifts its bond over by one position, I can go from a 3-membered ring to a 4-membered ring. That is less strain on the ring. In fact, this can even happen if I go from a tertiary carbocation. Then it becomes secondary over tertiary, but it's always in the aim of better stability, and in this case, it's ring stability, angle stability. That's not a methyl shift. It's an entire alkyl group shifting, and specifically inside a ring. This is one that I don't put on my exams or the unit tests, but it is an interesting application of carbocation rearrangements. By the way, we're going to be learning like 11 reactions with alkenes. You're going to be tested on the mechanisms for 4 of them. I could test you on all 11. I don't, because the 4 that I'm highlighting are the ones that I feel if you master, you'll have them down. If you master these 4 mechanisms, you can understand any of the other mechanisms. But if you can't master these 4, you're going to struggle with all of them no matter what. So I have a choice as your instructor. I can highlight 4 mechanisms that I feel give you the best foundation for understanding mechanisms from here on out. Or I can just ask you to memorize everything. So it's my executive decision to narrow down what mechanisms we learn in hopes of giving you the best chance of actually mastering them. Does that seem fair? If you're interested in being tested on the other mechanisms, let me know, and I'll give you special questions on your test. Okay, questions on the HX addition mechanism. There are 2 scenarios, with carbocation rearrangement, without. We've done both. Make sense? Okay. I want you to flip to the front page of that worksheet. You will notice that this is different, and I've updated it on Canvas. So if you had the old one downloaded from Canvas, I recommend. Oh, that's a bummer, because I really thought I had checked it. Okay, thank you. Let me fix that. You'll notice, actually, maybe you can see what I've changed. I had an 8-membered circle last time, and what do I have this time in the worksheet I gave you? Three groups of 4 reactions. The main reason that I did that is because I found my students last semester cramming a bunch of notes into the corners and making it really hard for them to actually go back and interpret anything about all of those reactions. So now I'm spreading them out, thinning them out. So you have more space to take notes next to them if you want to. But also, each one will draw your attention a little bit better. Oh, I see. I've got 2 different files with the same name. Love that. All right, Camilla, let me know if this updates it now. Okay. I also want to point out that I have chosen a specific alkene for most of these reactions. It is an alkene that shows regiochemistry. There is a less substituted carbon and a more substituted carbon. So when there is a regio difference, about two groups adding to specific degrees of substitution, less or more, this will highlight it. I also have given you an alkene which forms a more substituted carbocation that can undergo carbocation rearrangement. So when carbocation rearrangement is possible, you will see carbocation rearrangement. I want you to be aware of when it is possible and when it is not, because that changes the mechanism that you should expect to show. We already did HX, and what do we notice about HX? Rearranges. It has the capacity for rearrangement. So a note that I want you to leave for that. Carbocation intermediate. If you don't show a carbocation intermediate, you're not showing the reaction. If you show a carbocation intermediate, you should really consider whether it can rearrange. Still? But didn't yours have this issue last time? What solved it last time? Shoot, I'm sorry. Maybe you can take your notes on something and then just copy and paste them later. I'm sorry. Here are some other things that I like to point out. Regiochemistry. I'm going to abbreviate regiochemistry with R. This is a Markovnikov addition product, which means hydrogen goes to the carbon with more hydrogen. Useless. Okay. Maybe. No. Carbocation forms on the most substituted carbon. That's what Markovnikov missed. And because there's a carbocation, there's the potential for rearrangements. But Markovnikov's rule just means hydrogen adds to the carbon with more hydrogen. CH2 becomes CH3. Okay, stereochemistry. I'll abbreviate that with S. If the hydrogen adds and forms a chiral center, it leaves behind a carbocation. What geometry does a carbocation have? Trigonal planar. It's flat, which means the nucleophilic attack can happen from the top or from the bottom. And so if that creates a chiral center, it is irrespective of the chiral center that the hydrogen already formed, which means the hydrogen adds to a flat alkene, top or bottom, and then the nucleophilic attack happens to a flat carbocation, top or bottom. So you get mixtures of all possible chiral centers. So the stereochemistry of this is random. If chiral centers form, they form irrespective of each other, and you get all possible combinations. Which, by the way, on the second page, I've got numbers next to these reactions. That's telling you how many structural or stereo isomers can form, or both. That is, what combination of regio and stereochemistry can you have? That's what I'm telling you in that parentheses, how many different products you can form. All right, to the top right, you can see that this is not HX addition anymore because across my alkene, I've added two X's. This is X2 addition or halogenation. In a lot of places, you may see a solvent listed here, like THF. Do you remember what category of solvent tetrahydrofuran lived in? Tetrahydrofuran was a 5-membered ring with an oxygen. Polar, aprotic, which means that it plays no role in the reaction. So listing THF, superfluous. It doesn't really do anything. Does X2 addition have any relevant, or sorry, does X2 addition have a carbocation? Does the intermediate put a positive charge on a carbon? Why? How can you know by seeing the product? If there was a carbocation, like last time, there would have been a rearrangement. I know there was a rearrangement here because that tertiary carbon that holds the halogen that added was not involved in the alkene. If a carbon not involved in the alkene is going to go through a chemical change, there must be a rearrangement. Here, it's just the 2 carbons of the alkene. No rearrangements, no carbocation. The regiochemistry does not describe hydrogen at all. There's no hydrogen involved, so I can't use Markovnikov and I can't use anti-Markovnikov. So here's what I point out. The regiochemistry here is a vicinal dihalide. Do you guys remember what that term means? Vicinity. These are in the same vicinity as each other. A 1,2 dihalide is a vicinal dihalide. Stereochemistry. This alkene that I've selected, it doesn't do a great job of highlighting the stereochemistry of these reactions, which is why some of the mechanisms we do will. The stereochemistry here is anti-addition. This reinforces that there is no carbocation intermediate, and the mechanism will help us understand that. So I want to take a deviation now to look at the mechanism for X2 addition. So if you would go to the last page of your worksheet. On top, we have 2 different reactions. How many steps for these reactions? Oh, not a trick question. 2 steps. No more, no less. 2 steps. Step 1 is described by the intermediate that it forms. Step 1 will form a halonium ring. That suffix, IUM, what does it indicate about a structure? Sodium, calcium, hydronium, ammonium, positive charge. That IDE indicates a negative charge, fluoride, hydride, oxide. IUM indicates a positive charge, ammonium, calcium, sodium, halonium. So step 1 is going to have a halonium ring formed. By the way, what should I write over the reaction arrow for this? Bromine, elemental bromine, Br2. I will describe that sometimes by its legal name. Elemental bromine. Do you know why we call it elemental? That's how you find it in nature. As only bromine, it comes diatomic. That is its elemental form. All right, step 1, halonium ring. I'll give you a hint. The halonium ring is a 3-membered ring bonding to a halogen. So we can specifically call this one the bromonium ring, or if we're using chlorine, a chloronium ring, iodine, an iodium ring. In order to form this 3-membered ring, this ring is going to form on only one face of the alkene. And I'll need to balance charge. If I create a positively charged ring, I'll need to have a negatively charged structure somewhere. That means bromide will have to form. How do I form bromide? The bromine-bromine bond has to break. Heterolytic cleavage. One of the bromines keeps the electrons. The other is going to involve in the halonium ring. Spot the difference. Carbon-carbon bond breaks. 2 carbon-chlorine bonds, 2 carbon-bromine bonds form. I can use the carbon-carbon bond to form one of those carbon-bromine bonds. Where does the other carbon-bromine bond come from? Bromine goes from 3 lone pairs to 2 lone pairs. Jordan, does it have an octet on the right?
What?
Does the bromonium have an octet?
I don't know.
Somebody help her out. Kirsten?
Yeah, because it has 2 bonds that have shared electrons, and then it's got 2 lone pairs, which is 8.
Good. 2, 4, 6, 8. Perfect. Positive charge, funky, but it's still an octet.
Why does it have that positive charge?
Because it's sharing more than it would like to. Bromine's great. Halogens are great at sharing 1 bond and keeping 3 lone pairs for themselves. They're not great at sharing 2 bonds. That is less electron density than it prefers to have. Okay, so bromine needs to lose a lone pair. That means that it needs to share its lone pair with a carbon. Then the carbon-carbon bond can share back. This is how I like to describe it. Bromine attacks one carbon. Its brother attacks the bromine back. 2 carbon-bromine bonds form in one step. 1 from each direction. 1 from bromine, 1 from the carbon. 1 carbon-bromine bond, 1 carbon-bromine bond. Step 1. Step 2. We call this a backside attack. We call this a backside attack because it is stereo-specific. This bromine is sitting on top of what used to be a flat alkene. If I could show this on its side, it looks like this. That used to be a flat alkene, and the bromine is just sat right on top. Well, the second bromide wants to break open that ring. In order to do that, it has to put electrons into the sigma star orbital, the anti-bonding orbital for carbon and bromine. That means that the sigma star on carbon is underneath. It has to attack from directly opposite where the bond is. You might think of this like trying to push somebody out of a taxi cab from the back seat. You're not going to climb over them on one side and then kick them out that same side. You're going to climb in from the opposite side of the taxi and kick them out. Bromide is not going to come from the side bromine is already on. It's going to come from underneath where there is less sterics, less repulsion. So we call this the backside attack because bromide comes from underneath. I don't think any of you, I'm not sure if you guys got my taxi cab analogy there. Bromide. I want to pay attention to the stereochemistry. Do you guys agree that the intermediate I drew was wedged? I could have drawn this dashed. It's meso. I could have flipped it around. It would have looked exactly the same dashed. I want this carbon on the left to keep its dashed stereochemistry. I don't want to break that bond to the carbon on the left. I actually want to break the bond to the carbon on the right. I'm showing the formation of one possible product. There are different possible products. Bromide attacks carbon. Carbon-bromine bond breaks open to bromine. Why does bromine take the carbon-bromine bond? More electronegative. Pulls the electrons to itself. In doing a backside attack, the new bromine has opposite stereochemistry of the old bromine. That's why we call it a backside attack. If bromine was on top when it was in the ring, the new bromine is going to be on bottom when it breaks open that ring. By the way, if you don't want to call this backside, you can call this ring opening. That also describes what we're doing. Is that the same structure that I drew above as the product predicted? It is, but it's in a different conformation. This is in a zig-zig conformation. The structure given was in a zigzag conformation. Notice how the bromines here are positioned anti to each other. That's why this is an anti-addition mechanism. The backside attack led to the bromines being added across different sides of the alkene. But because this is a linear structure, it's free to rotate into different conformations. So after it rotates, you can't explicitly see that it's anti, but the only way for it to do a backside attack is if the addition is anti. So this simply rotates just like we practiced back in Unit 2. When I rotate this zig-zig into a zigzag, my dashed group comes up looking wedged. It has the same chirality, same absolute arrangement in space. It's just twisted around itself differently now to take up a lower energy. 2 steps, a total of 5 arrows. That's it. Okay? By the way, if I gave you this exactly and I said draw the mechanism and you got to here, full points. Because this is that. You don't have to show me the conformational rotation, right? Okay, I realize I didn't give you guys a break today. Sorry. We're going to keep going. There's a second one. I want to move on. At the start of class tomorrow, I'd like to see your solution tomorrow. At the start of class Wednesday, I'd like to see your solution to the anti-addition of chlorine, the chlorination of cyclopentene. Okay? All right, back to our flow chart. To the bottom right, we form a halogen and what other functional group? Allie? No? A methyl? I think that's an R, so hard to know if it's methyl or isopropyl or phenyl, or it could be a lot of stuff. ether. Here we form an ether group. An ether next to the halogen. Carbocation? Any carbocation in the formation of this? Because if there was, we'd see a rearrangement to that tertiary carbon for one of the groups. No carbocation. The regiochemistry is a vicinal halo ether. This is called the halo ether addition because I'll add one halogen, but I'll also add an ether group. And to highlight the regiochemistry, the halo group will be less substituted. The ether group will be more substituted. Markovnikov really missed something here. He could have had every single one of these reactions named after him if he had better pinpointed how charge led to placement. But instead he focused on the hydrogens. So, not to beat a dead horse, or a dead guy. Stereochemistry, anti-addition. Remind you of something? Yes. It reminds you of the halogenation reaction. This follows almost exactly the same mechanism. But there's one difference. Over the reaction arrow, we have X2 and a solvent. And that solvent is what? Layla? Alcohol. If I react X2 in the presence of an alcohol, the alcohol plays a role. Do you remember what we called reactions where the alcohol is engaged? Britton? Not where the alcohol, sorry, where the solvent is involved. That was how I meant to set you up for it. Vivi? Solvolysis. So this is a solvolysis reaction where the solvent is actively engaging in the reaction. You guys did that today, actually, right? You used you used water as a solvent in your substitution reaction. It was present to a large amount, and that water solvent reacted to give you an alcohol byproduct. Okay, or an alcohol product. Okay, similar to this but distinct is if I have X2 in the presence of water. Notice that there's still no carbocation rearrangement. This is a vicinal halohydrin. The hydrin is indicating that you have water. Or I'm sorry, that water was the solvent and that you have an alcohol in the product. Once again, where the solvent has engaged is more substituted.
What was that saying?
Halohydrin. Hydrin. So what's the difference between getting an ether in my product and an alcohol in my product? What do I need to change to get that difference in functionality? The solvent. Alcohol as a solvent is a precursor to ether. Notice how I lose the hydrogen on the alcohol. Carbon-oxygen bond, very strong. Oxygen-hydrogen bond, very easy to lose. Water is a precursor to alcohol. What did I lose? A hydrogen. Both of them lose a hydrogen from the solvent. So if I want an ether, I need to have an alcohol. If I want an alcohol, I need to use water. These mechanisms are identical. So this will be the bottom of our last page. What reaction is shown on the left? Halohydrin addition or haloether addition? Halohydrin addition. What's shown on the right? You guys seen it on the very last page on the bottom, the last two reactions. Haloether addition is shown on the right because I form an ether byproduct, OMe. Okay, let's go through the reaction on the left. What reagents do I need over the arrow to form that product? Go ahead and shout it out. Elemental bromine. Water. Why can't I use elemental bromine and ethanol? Ethanol is an alcohol, will lead to an ether. I want an alcohol. Water is the precursor to alcohol. Br2, H2O. How does the first step compare to the halogenation mechanism? One more time for me. Exactly the same. So when I draw out my reagents, I'm going to show Br2 and H2O, but recognize that H2O doesn't play a role yet. Show me the formation of the bromonium ring. Oh yeah, okay, so on canvas, or sorry, on active, where you place the arrows attacking to and from, they will grade you on. I won't. As long as you have appropriate arrows, then where they attack and where they come from won't be as important. But do you remember that there is a partial charge difference across a more substituted and a less substituted alkene? Where's the partial positive? On the more substituted. So when the bromine lone pair attacks, where does it attack? More substituted. Electrons always go to a partial positive. So when bromine attacks, we can show it attacking more substituted. The less substituted carbon is used to attack the bromine. If this is the product that I want to form, there are different stereoisomers that form. If this is the stereoisomer I want to form, should I draw the bromine wedged or dashed in the bromonium ring? Dashed. This bromine is going to add on, and it's going to stay there. So I want it to stay dashed. Positive charge on bromine. I form bromide. Water does nothing.
Are all three of those arrows supposed to be there, like from the bromine, the electron, the pair? Is it supposed to go to that form?
Okay, so I would accept if you had the bromine lone pair go to either of these.
Okay, but we do need to show that.
Well, yeah, that's how that bond forms.
Well, but isn't that the bond to the Br?
That's how the other bond forms.
Oh, okay.
There are two bonds to the bromine, so I do need to have two arrows showing those.
My question.
Good question.
So one of those is showing that the bromine is.
One is showing the bromine is attacking, and it makes sense to have the bromine attack where electron density is low, at the more substituted carbon. And one is showing the bromine being attacked. Again, like just two dudes buffing it out, you know? Equal punch, swing, same time. Okay, What's my second step? Come on, you guys can read. Backside attack. How does that compare? Exactly the same to the halonium, to the halogenation. You remember how I said I'm asking you to know 4 mechanisms? I'm basically doubling up on some of them. The halogenation mechanism and the halohydrin and the haloether, those are all the same, except this will have one additional step. All right, so I've got my bromonium ring. Bromide does not play a role here, but instead water will. I get this a lot, which is if bromide was able to react in halogenation, why doesn't it react now? In all reality, it can. If you have a small amount of reagent, like 600 billion molecules, so just like a millimole, 600 billion molecules can react in a lot of different ways, and there is a non-zero chance that bromide does react. But water is the solvent, which means that it's present to at least a million-fold excess. So there you've got a 1,000,000 to 1 chance that water is able to beat out bromide in a nucleophilic attack. Water attacks at the more substituted carbon, breaks open the bond on that more substituted carbon. Why do you suppose water attacks at the more substituted carbon? More substituted, better partial positive.
You would show it directly off the oxygen. You would show like oxygen to hydrogen.
Oh, the OH bond is not breaking. Yeah, good question. The OH bond is preserved. So what we get here is a dashed bromine on the less substituted carbon and a wedged OH2 plus. Thus the last step. We're not done. What do we need to do? I don't have an alcohol. I have a protonated alcohol. I need to deprotonate that alcohol. So last time, the first time I introduced acid-base, I put in parentheses protonate. That's what we did with HX. We protonated the alkene. This time, you could actually refer to this acid-base as deprotonation. Remove the proton. What will act as the base to deprotonate? Bromine's not a bad guess. Or sorry, not bromine, actually, right? Bromide. Bromide, as a base, becomes hydrobromic acid, which is not a very good acid, or sorry, which is a very good acid, which means bromide is not a very good base. So you could plausibly add another another water molecule in here. Water is actually a better base than bromide. Where would that water come from? The solvent. Remember, we have a 1,000,000-fold excess. We're just selecting the smallest number of molecules to exemplify the reaction. Bromide, though, definitely can act as a base, and if it did act as a base, it would just protonate water somewhere else. So this is a plausible option I'm happy to accept. Bromide takes the hydrogen. OH bond goes back to oxygen. I'm not sure that I answered this. I might have skipped it too fast. Why did water attack the more substituted carbon? Oh, I think I did answer it. Better partial positive. More substituted, more positive, more willing to be attacked by a partial negative. So this has regiochemistry, and if Markovnikov had just figured that out, he could have expanded this to say partial negatives attack the greatest partial positive. Partial negative attacks the greatest partial positive. And then everything would have followed Markovnikov's rule. But instead, he's got these things that apply, things that are anti, and things that don't apply. Jordan, you've got a question here.
Yeah, wait, can you just explain, because you were talking about water, but then the arrow coming from the drone.
Sure. So you'll notice that I only drew one molecule of water throughout this, right? There's like a million more. So if I wanted to, at this point, I could draw another molecule of water, and I could show that new molecule of water acting as a base. It would just change what my byproducts are. I'm realizing I didn't actually draw my byproducts here. Here I'd have hydronium bromide, and here I have hydrobromic acid. Hydronium is actually a weaker acid than HBr. So if HBr even forms, no, it doesn't. It just gives away its hydrogen to a nearby water molecule. More likely, but not implausible. This might happen. Show either. Both are lovely.
And then the oxygen in the water has a positive charge. It has a full octet.
Yes.
2, 4,
If it helps, how many lone pairs did I draw here? Just one. How many does it have? 2. Uses one of them to form a bond, so how many does it have? Just 1. That's why it wants to break its bond with hydrogen so that it can reclaim its second lone pair. Yeah? So, one more time. What's the difference between halogenation and halohydrin addition mechanisms? The acid-base step. And the nucleophile that does the backside attack. Change the nucleophile in the backside attack and then deprotonate that nucleophile. What if I had not done this with water as a solvent? What if I had run this in methanol? Well, all of a sudden, throughout the whole mechanism, everything that said water changes to methanol. And here, I get a protonated ether instead of a protonated alcohol. And guess what? Nothing changes. I still just deprotonate my oxygen. So what's the difference between a halo ether mechanism and a halohydrin mechanism? Nothing. Literally nothing. They're exactly the same. It's just whether the oxygen is attached to a carbon chain or is not attached to a carbon chain. Okay? So I consider those the same mechanism because there is literally no difference. So we have learned HX, X2, X2 in polar protic solvent. We've learned 3 of the 4 mechanisms. We've also learned 3 of the 4 reactions. I'm running a little bit low on time, but I want to tell you the next one that we're going to run. In the next set of 4, on the top right, do you guys notice the alkene in the middle? It's the same alkene. So we get those same principles of if there's a carbocation rearrangement, we'll see it. If there's regiochemistry, we'll see it. But if there's stereochemistry, it doesn't do a great job highlighting it. The next one that we'll look at is called acid catalyzed hydration. Is there a carbocation in this mechanism? So what other mechanism that we've already learned does this resemble? The HX addition. But what difference will it have from HX addition? it will require a deprotonation step at the end. I'm asking you guys 4 mechanisms, but really it's like 2 sets of 2. HX and acid catalyzed hydration, they're very similar. One just requires deprotonation. Halogenation, halohydrin, haloether, they're very similar. One just requires deprotonation. So we'll start with that mechanism. If you want to get a jump start on it already, you're welcome to. I would love to come in Wednesday and look at your chlorination mechanism of cyclopentene and your haloether mechanism of 2-methylpropene. If I can come in and get you to show me those mechanisms, I'll even start by having them on the board, and before I turn on the camera, you guys can come and add the arrows. That's how we'll start class Wednesday. Then we'll do this mechanism, and then we'll spend time with getting familiar with reagents, identifying the changes in functional group, learning the regio and stereochemistry of the reactions, and applying them. All right? Don't waste time. Practice these mechanisms tonight.
Can I ask you a question?
Please.
On these you're saying like no carbocation ring and stuff. Every time that high bond breaks, isn't there a cation that forms though?
No. A cation, maybe, but not a carbocation. Take, for example, the halonium ring. That's a cation. The positive charge is never on the carbon. That's important. Thank you guys for your time. It's great to be back. You got a follow-up on that, Jordan?
I'm just like if that bond
Thank you.
breaks,
Thank you.
that bond breaks right between those 2 carbons. And the electrons go to one side or the other.
Well, yeah, here, the electrons went to the less substituted, and they were used by that to attack, but at the exact same time, the bromine attacked back. So,
So it depends on if something is also happening, like taking that spot.
yeah. Yep, it does. If something else is going on, there's a lot of changes that can happen. We haven't looked at what happens when something attacks the alkene and gives a negative charge on one carbon. We've only looked at when the alkene attacks and leaves a positive charge on one carbon. And here, where one carbon attacks and is attacked at the same time, and so nothing happens, but both carbons change. A lot of fun stuff.